Yeah.
Okay, you ready?
Yeah.
Okay. All right. So here's where we're at in our journey to physics enlightenment. So we figured out how to do physics. Okay, here's what we're going to measure, what units we're going to use. Here's how we're going to do labs. Here's how we're going to write answers. Here's dimensional analysis, all that good stuff. So now that we've got that done, now we can actually start to do physics, okay? So the first broad topic in physics is called kinematics. Kinematics comes from the Greek word meaning motion, okay? So we'll talk about like kinetic energy eventually, which is the energy of motion, okay? If some of you want to study like the human body, we'll take a class called kinesiology, which is basically the study of human body and how it moves, okay? So we're starting like a trifecta of chapters. So, and they all build off of each other. So the first one is velocity. So we more so than any other unit we will study, you have to have the vocabulary right. So we're going to lay a very solid foundation of what it means to talk about velocity versus speed or displacement versus distance, okay? Because if you don't understand velocity, then you can't do the next unit, which is acceleration. Well, acceleration is the change in velocity. So if you don't know what velocity is, then you don't know if it's changing, okay? Well, the next unit is force equals mass times acceleration, a whole unit on forces. So if you can't do acceleration, you can't multiply that by mass to get the force. So you got to have velocity to do acceleration because you got to have acceleration to do force. So we have to establish a very solid foundation with this stuff. So when you look at this whole concept of velocity, it oddly enough starts with how you define where you're at. Okay? That's the first thing that you have to define. Because if you don't know where you're at, then you don't know if your velocity is changing or if your velocity is constant. Okay? So let's say max. Where is your position in the room? If I said, okay, hey, I need to find, Mr. Botts needs to find Max. He calls me and says, hey, I got to find Max. Where is he in your room? What would you say?
Right in the middle.
Kind of close to the front.
Huh?
Kind of close to the front.
Kind of
Considering
close
that
to the front.
That's a lot of your room back there as well. So pretty close to the front of it.
Pretty close to the front of the room. There's a lot of things that are pretty close to the front of the room.
I'm in the
Okay.
second row of tables. in
Second
the-
row. From where?
From your
From your desk.
So you're establishing, we're going to let the desk kind of be the reference point.
Yeah.
I'm exactly
Okay.
where I am. If I'm the
We'll
right.
see.
So you're saying that you're kind of close to the desk, okay? Again, in the second row back, again, there's a whole bunch of people that are in the second row back. You're not that special yet. We've got it narrowed down.
It's right behind the camera.
Well, see, now you
Now
changed it,
the camera is the point of reference.
okay?
not the desk.
Because initially he was describing his position relative to the desk. Now you've changed it and said, oh, I'm describing my position relative to the camera.
Can I describe my position relative to me and say I'm exactly where I'm at?
No,
Okay.
you can't be your
What's
own
better,
reference
the
point.
camera or the
Even
desk?
Albert Einstein couldn't be his own reference point.
Okay.
So, desk, camera,
Desk.
desk. Second row back, now what?
I am
One row.
sure one row.
Or one column
One
over.
column over.
One column over, which way?
Right.
From
My right, your left? My right,
Use
your
cardinal
left?
directions.
facing the back of.
Which way is this?
Pretty sure I'm north of you.
No.
Right? Am I?
That's north.
Yeah,
Yeah.
I'm north of him.
Yeah.
I'm north of the desk. 2 rows.
So north of the desk, 2 rows, then
and
what?
west of it, 1 row.
West of,
West of the desk,
how far?
1 column.
North
And then,
one foot.
and then I'm on the west side of that 1 column.
Okay,
Right? He's north 1 foot of the camera.
he's north, or he's just north 1 foot of the camera.
Yeah.
That's
Like
not
that's
a foot.
easier.
That's not a
the easiest
foot.
way.
Yeah, but
It
we
is.
want to make it difficult just because we can.
No. But here's the point. Which one is a more valid description of where Max is? 1 foot north of the camera,
It's more precise.
or he's 2 rows back from the desk and then 2 columns to the west.
They're both valid.
They're both valid. Is one more right or wrong?
No.
No. okay?
Let me know.
They're both out. You could pick any point in here. You could pick the new water cooler. You could pick the F equals MA sign. You could pick the stapler, okay? It does, you're not gonna pick the Communist Manifesto.
It's my point of reference.
Huh?
It's my point.
I don't care if it is your point of reference. It's no, okay?
These pretty prairie kids are gonna question me.
Maze is already red.
No, I went out,
Yeah,
I went out there
communist
last night, and
image.
met with the principal after school, and I already told him, I said, this is kind of an eclectic bunch, so, you know, you just kind of gotta roll with the punches, and, you know, God knows, you know, the random conversations that you're so, like, because there's only like 2 kids out there that are taking class, so, yeah. What, Matt?
It's nothing that you would want to hear.
Max keeps on
Okay,
saying stupid things.
guess what? They're gonna hear it on the camera. So if you don't want me to hear it,
No, it's not that I don't want you to hear it. It's something that you would be disappointed in me for hearing. So you don't want to hear it. It's two different things. It's nothing.
okay, all right. So, how you pick your frame of reference is going to determine how you're going to describe the motion. So Max, right now, what is your velocity
Relative to this room,
relative to this room?
0.
0. Why?
Because I'm not moving relative to the room.
Yes, his position, Logan,
I'm sorry.
is not changing relative to the fixed point, okay? We'll call the point of reference, okay? The reference point, however you want to put it. So, he picked the desk, he picked the camera, whatever it is. His position is not moving. Now, could we change the perspective and say, oh, Matt's actually going pretty fast? Max is actually going pretty fast.
Well, if you're looking at it from space.
Oh! So, we're on a rock that's spinning, right? Okay, at the equator, you're at about 460 meters per second, where we're at about 400 meters per second, because we're closer to the North Pole. So, we're at about 400 meters per second, faster than the speed of sound. But you don't have that sensation that you're going faster than the speed of sound, right? Because everything is moving with that. And it's cool that this rock that we're on spins, because if it didn't spin, one side of the Earth would always be facing the sun, and one side of the Earth would always be facing away from it. So you'd have half the Earth basically in a sheet of ice, and you'd have the other half continuously being baked by the sun. And so you might have like kind of a strip around that whole thing where you might be able to have like, you know, kind of this continuous twilight zone. It'd be really weird because it would be like continuous sunset or sunrise, depending on which side that you're on. So,
They're really cool.
That would be cool.
well, no, it wouldn't. No, no.
Do you not enjoy the orange of the sunrise?
Have you never
I
seen
do, but
the
it's like
Twilight
every
Zone?
day. I mean,
No,
it
you
never
don't.
changes.
Just
There would be no
move
day.
then. You can go all day light.
Oh, vacation. Oh, here, let's go on a vacation. We'll go to the dark side.
Night goggles.
We'll go to the light side.
Oh, you need some night goggles and sunglasses. You're fine.
Okay. there
Make
we
it a day trip.
go. Yeah, literally. Step across the line. Oh, we're in dark side. So, if you change this perspective, like Honda says, oh, hey, the Earth is spinning, Max is moving with it, here we go. Can you change that perspective even more?
We're spinning around the sun.
Huh?
We're going around the sun.
We're going around the sun. We're on a rock that's orbiting an average star in an average galaxy. Okay? So if you change the perspective and go, okay, not only is Max on a spinning rock, that rock, as it spins, is also going around a star. Okay? Now, you can make it even bigger. We're in the Milky Way galaxy, spiral arm galaxy, right? Spiral arm galaxy is orbiting a massive black hole, we think, at the center of the Milky Way galaxy. Guess what? So now our star is being dragged around as part of the Milky Way galaxy. So we're moving that way. Guess what? The Milky Way galaxy itself is moving through space. So we're also being dragged along as part of the Milky Way galaxy, which is moving through space, which is eventually going to collide with the Andromeda galaxy. And that's going to get real ugly real fast. But don't worry about it, we'll screw up this Earth way before then, okay? So don't go home like, oh God, so much for graduation, our galaxies are colliding with
Gotta
the
get that
Andromeda.
single-use plastic.
Yeah.
What?
Well, you said we're gonna ruin the Earth.
Gotta get
I'm
that
helping right
single-use
now.
plastic.
Why are you bragging about that? I don't like
I
it.
recycle them.
Just refill it each time. There you go, that a boy. Okay. No.
With the following students, please come to the front office. Isabella Singh, Ariana Labardi, Haley Harbinell, Lauren Furman, and Alina Cunningham.
Here's what's weird. I can't hear the morning announcements, but I hear announcements that are only supposed to be broadcast in the Commons.
Oh, that's what that is?
Yes.
Oh, I was gonna say that only happens in this class. Yeah.
Yeah. No, that's supposed to be happening, that announcement was supposed to be in the Commons.
That's weird.
But I can't hear like the morning announcements that are broadcast over the whole school.
One of your old students played the greatest prank of all time.
No, that wasn't the greatest prank of all time.
No, one of the best ones.
No.
One of the best ones at the
Then
school.
what's the greatest prank of all time then?
I don't know yet, I haven't come up with it.
Flipping the school
Okay.
upside down.
The Earth is
We
round,
gotta
it's really
do it.
flat.
Yeah. Okay, so here's my point. Depending upon your perspective, okay, you can either go from Max is at rest or Max is on a rock, part of the Milky Way galaxy, which is headed toward a collision course with the Andromeda galaxy. Okay? I mean, that just depending upon how you view the system. Yes?
What would happen when our galaxies collide?
Thankfully, most of our galaxy is empty space, so it isn't like you're colliding two things. But if you look at the computer simulation, the wild card is what's going to happen, assuming that there's a black hole in each one of them. If the black holes collide, then that's going to release more energy than basically that would be imaginable. And basically everything is going to, any planet that would have an atmosphere, that atmosphere is going to get blown away because of the fact that it's going to release so much energy. So,
Could you imagine just everybody dying the same day?
huh?
And getting destroyed by...
It'd be a cool thing to watch until it wasn't.
So,
No, yeah, that'd be awesome.
Yes.
Well, you wouldn't be able to watch it until you
Huh?
could.
what would we have to do to survive that?
Oh, you get out.
Yeah,
You
you're
get
done
out.
for it.
Wear spacesuits and still,
No,
No,
you are
no.
done.
we're done.
Get out.
We go to Avatar.
Last Airbender or
But
No,
believe
the
me,
blue-
our sun is going to run out of fuel before that happens. So, it's kind of a deep, we'll talk about it later.
gotta
Okay.
refuel
Not
that
if we
sun.
plug it in.
Now,
Have some hydrogen.
what'd you say?
Not if we plug it in.
The sun. Just hook it up
That's
to
the problem.
Hook it up to
We
a
had,
quick trip.
somebody unplugged it. Go get that extension cord. We'll get the generator.
Get up to a
Okay.
quick trip.
Anyways.
We were in Greece.
What the heck? It keeps turning.
Huh?
We were in Greece and I can be a genius.
But we're not.
It's the freaking the cord is pulling it.
Okay.
The cord is like turning it. The weight of the cord.
All right.
Nice band.
No, it's not.
They keep laughing at your election stuff.
Great.
I'm kidding.
I'm laughing at him because his stupidity.
All I said was,
No. Huh?
all I said was imagine it, like we die and then billions of years after, like there's no more Earth.
Yeah. It's going to happen. The Earth is going to get consumed by the sun. It's going to happen. So, we won't be around to see it. It's like 5 billion years out. So, give or take 10 minutes.
You check that out.
Yeah. Okay, now, so back to some real science. Okay? Not that astronomy is, but it's too far out in the future. So here's the deal. Let's say I throw Gary the golf ball up in the air, right? So how could you describe that motion?
It's not moving in the room. It's moving around it.
Backspin? Okay? So then you're talking about the motion relative to the axis of the golf ball itself.
It
Okay?
has a positive velocity.
Has positive velocity
Yeah.
in both directions.
Up.
So Honus is saying it has a positive velocity going up. Okay? Well, if it has a positive velocity going up, then coming down it would have to have a
Negative velocity.
negative velocity. Now, So Honus has arbitrarily decided up is positive and down is negative. It's arbitrary, okay? He could have said, I want up to be negative and down to be positive. Okay, cool, valid, all right? Because it's however you want to define the system. Now, but what do you want the reference point to be as I throw that in the air? We could have the ceiling be the reference point. If the ceiling is the reference point, how would you describe the motion?
You're throwing it down, and it's going up.
Well, it's going, if that's the reference point, then you would say it's going
Toward the
towards the reference point and then
away.
away from the reference point. Now, but if my hand is the reference point,
It's going away and toward.
then you say it's going to go away and then back down. Both descriptions are equally valid. It's just how you want to define that system. So, Honus brought up an interesting idea. This is this concept of positive and negative. So, the first bit of terminology that you have to understand is something that's a scalar quantity versus something that's a vector quantity. I promise you, on the next test, I'm going to ask you, what is the difference between a scalar quantity and a vector quantity? I promise you, I'm going to ask you that question. And when I do, here's the magic word that I want to hear. I want to see the word while. So you would say, a vector quantity has two things, magnitude and direction. So magnitude is just a number, okay? The direction says, oh, you're going north, south, positive, negative, 120 degrees, whatever it is. So vector quantities have two components to them, magnitude and direction. Scalar quantities only have a magnitude, okay? So here's what you would say. Vector quantities have magnitude and direction, while a scalar quantity only has magnitude. Okay, so anytime you're asked what's the difference between two things, it's always nice if you include the word while. Okay, so like what I'm going to be talking about position time graphs. I'm going to say, okay, hey, how is constant velocity shown on a position time graph, and how is that different than accelerated motion? And you would say, oh, constant velocity is a straight sloping line, while accelerated motion is a curved line. Okay, so anytime I ask you to compare things, use that word while. That's a nice way to look at it. So, quick little video clip here.
Do we need to record this?
Yeah, just keep it running. Just take a second.
You're not the one running the camera. Why are you asking that?
Well, I wasn't sure if they'd pull up a video there.
Well, you can do that. I'll put his editor. Yes. It's right there. It's right up there. Right there.
Hold on. I've lost that.
This is gonna be like a Bruce base.
Here we go.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
Okay, if any of you do that on the test to demonstrate this, I will flunk you. All right. So, no. If you get the urge to do that, don't. Okay? Just say no. Just say no. Now, and here's the cool thing, and I know this is up here, and I'm going to read this up here, because I had one of my former students make this. Vector is a quantity represented by an arrow with both direction and magnitude. So if you're on the test and you go, oh man, I forgot. Look, there it is. Okay? And go, Burkamp, do you know that's up there? Yes, I know it's up there. It's cool. I'm going to leave it up there. I'm not going to cover it up with a piece of paper. I know it's up there. So, hold on. This is going to... Okay. All right. So, there are certain classic things that are going to be vector quantities. Displacement. Okay? So displacement would be, okay, Max is going to get up and he is going to walk in a particular direction. He's going to walk to the east 5 steps. He's going to walk to the north. He's going to jump up in the air. Okay? his position is going to change. So one of the things that's important out of this deal, and this is all about terminology, is that if you're going to change position, there is no exceptions to this. It is always position final minus position initial. Depending upon the numeric values, change in position, otherwise known as displacement, might be a positive number, it might be a negative number. So here's one of the things I want you to get out of your mind right now. That negative displacement means that you're going backwards, and positive displacement means that you're going forward. It's arbitrary, okay? So, and positive velocity does not mean that you're going forward, and negative velocity does not mean that you're going backwards, okay? It's arbitrary how you define the system. So do not associate positive and negative with forwards and backwards or anything like that, okay? You'll see why it doesn't make any sense, because how you define your system is going to completely change the signs of those numbers. Okay, so Max's position within this frame of reference is not changing. He gets up and he walks. So then I can begin to talk about velocity. Velocity is going to be a vector quantity, because I can say, okay, hey, which direction is Max going? Is he moving to the right? Is he moving to the left? If he's moving really, really slow, we'll draw a smaller arrow. If he's moving really, really fast, we'll draw a bigger arrow, okay? And so the length of that arrow is going to indicate two things. Or the length of the arrow will indicate how fast he's going, and we point that arrow in whichever direction he's going, okay? That's it. Simple as that. Now, when you look at one of the great thought experiments that Albert Einstein did, he used a lot of trains, because that was kind of what they did back then. And so imagine that we've got a train here, okay? And Mary is sitting inside the train, okay? And, right, there's Mary, right? Trust me, that's Mary. Looks good, Larry, but there's Mary, okay? And Mary's sitting on the train, and the train is going in a straight line at a constant speed, okay? Straight line, constant speed. So imagine Mary sitting here, okay, right? Doing what Mary does, okay? And she's got a golf ball. The train is moving, constant speed. Now, she cannot see outside of this window, but we can see in. But she cannot see outside the window. The only thing she can see is what's happening inside the train. Now, Mary, you're sitting here and you're going to throw this ball up in the air. How are you going to describe the motion of the ball?
From my hand.
Yep.
Up.
Up?
Up.
Straight?
Yeah.
Straight back down.
Yes.
So if you throw it straight up, it's going to land back in your hand.
Yes.
Short, certain.
If I threw it right.
Yes. Okay, yeah. And assuming that you are, you can throw it right. So Mary's sitting here blissfully going, oh, the ball goes straight up, the ball goes straight back down. Okay? Boom, here you go, right? Now, Honus is standing here and he's seeing the train go by. And because he can look in, so he's going to see Mary throw that ball up in the air. How are you going to describe that? How are you going to describe the motion?
I'm going to say it's going up, but it's also traveling to the wherever the train is going.
Going that way?
Yeah. So it'd be traveling to the left as well. So,
Okay? So you would see it going like in a parabolic curve.
yeah.
So within Mary's frame of reference, the ball goes straight up and it comes straight down. But Honus on the outside looking in sees the ball travel in a parabolic curve because he sees the train and Mary going in that direction. So you have the same event happening. Honus says it's a parabolic curve. Mary says no, it goes straight up and it comes straight back down. Who's right?
Both.
Both. So this is the beauty of this, is that depending upon your perspective, you can have the exact same event happening with two completely different descriptions. Both of them are equally valid, depending upon your frame of reference and how you're viewing the situation. So this is why you have to be very specific about when you talk about velocity. What is your frame of reference? What's your reference point? Okay, stop that. We're done for today.